Welcome back. This is 6.2b, the DTFT relationships to Z transform. There is a close relationship between the Z transform and DTFT of a discrete time signal x of n. Why is this so? Let's examine the equations defining Z transform. The Z transform of x of n is this equation, which takes in the entire sequence of x of n and multiplying by z to the power of minus n, where z, as you remember, is the complex number. Now, when we say it is the entire sequence, it goes from n equals to minus infinity to infinity. Of course, in typical examples that we show you, x of n would have finite support, and therefore we can do this sum, or x of n is periodic, then we can resort to the DTFS equation. But never mind, let's proceed. Since this is a definition of x of z, let's see the definition of DTFT of x of n. Remember, DTFT, this is the equation specifying the DTFT, and if you compare the two, everything almost looks the same except for this guy. But when z is equals to e j omega, then z minus n becomes e minus j omega n, which is exactly this guy. Of course, we are using I here, where remember I and j are the complex number of square root of minus 1. So x of z and x of omega are actually the same when z is equals to e j omega. What does ej omega means? Well, it's actually 1 times e j omega, and then if you actually expand, it is 1 cosine omega plus j sine omega, and this number is on the unit circle for any omega that we put in. Or if you prefer, you just look at this as 1 with radius 1 and angle omega. It is nothing but this is 1 and this is omega. And then when omega is allowed to go from 0 to infinity or 0 to minus infinity, it is nothing but a phasor with radius 1, spanning the unit circle, where this is the real part of z and this is the imaginary part of z, and this whole thing is the z plane. So now we see that x of z and x of omega are the same when z is replaced by ej omega. But when can we replace this? When can we say let z equals ej omega? It is when the region of convergence of z includes the unit circle. So this unit circle, the region of convergence must shade this unit circle, and therefore we can say that these values exist for x of z. So please be careful. The z transform is only equals to DTFT when the region of convergence include the unit circle. Let's see an example. X of n equals to half n un, and then we know that by lookup table, x of z is equals to z over z minus 0.5. Of course, if you prefer the negative powers of z, you can then write it as 1 over 1 minus 0.5 z minus 1, simply by what we did was simply by multiplying this by 1 over z divided by 1 over z. Okay, so that's all we did. Now, we find where is the pole, and the pole is sitting at z is equals to 0.5 positive. So if you draw here, this is 0.5, and this is the real axis of z. So this is the real axis of z. And then now I use the green one to draw the imaginary axis of z. And then you'll see that at z equals to 0.5, which is here, we can draw a circle. And because the sequence is causal, we draw the region of convergence external to this circle. Because what we know is that absolute value of z must be greater than 0.5 in the region of convergence for this signal. Since the region of convergence includes the unit circle, then This expression can be converted into the DTFT simply by substituting z equals to ej omega. Well, here I'm substituting for the positive z, but you can actually substitute for the negative z as well. 1 minus 0.5 e minus j omega is the same answer actually. So it depends on whether you want to do positive powers of z or negative powers of z. It doesn't matter as long as the region of convergence of x of z include the unit circle. Now let's see the relationship graphically. The z transform is a three-dimensional shape. The DTFT is only the values on this red circle, and this red circle also forms a shape. Okay, so you should be able to extract these values and plot the shape. How does the shape look like? In the next page, this blue line is the magnitude response. It goes from a high value of 2 and comes down. And notice that I'm plotting the magnitude, so don't be confused. In this, I'm plotting in log scale, so you can't really compare one to one. You have to plot this scale as magnitude as well, so that will be 1 to 1. But what we are plotting is, we go from 0 to 2, in this example 0 to pi, and we see that the magnitude go from high to low. And then what you will see is that where is 0 to pi? 0 to pi is here. We go from 0 to pi. So it's 0 with a radius 1, and then we trace on this circle 0 to pi. And where is that value? It is somewhere from here and at the back. And then now it comes down. So this is the green, or well, maybe I should use a yellow, and then at the back, then comes down. Okay, so it is this amplitude that we're interested in. So it is a high value of 2, and then comes down slowly as we go from 0 to pi, which is this diagram over here. From 0 to pi, the value of 2 comes down, and this is the height of the surface of h of z. Now, remember that once you have h of z, you can express it in positive powers of z or negative powers of z. If you use MATLAB, please represent it as negative powers of z. So it's 1 over 1 minus 0.5 z minus 1. The coefficients of b and a are extracted from this expression. So 1 is here because this is its values is b1, b1, and this guy is a1, and this guy is a2. So this is a1, and this is a2, and this is b1, and then b0 is not b2. Sorry, b2 is nothing, right? So what is b2? So it's plus 0 z minus 1. So b2 is 0 here. Okay, so we don't need to put that. Anyway, you have this expression, b's and a's. You can use MATLAB's FV2. The word FV stands for filter visualization 2. You can plug in the coefficients, and then now you can see the magnitude response here, the phase response here, the pole and zero diagram, as well as the impulse response. So we use MATLAB to simply check our answers. Of course, you can't give us solutions of FV2 in the exams, but what you can do is that you can solve it and check. So where's the poles and zero? See? So the pole is here. Alright, with that, thank you very much.